All right. Last chance on questions from phase diagram one. Anybody write anything down? We're going to review it and have questions for me on Thursday, maybe. All right. This is the stuff that I actually cut out a little bit of your phase change. But this is this is a really cool equation. I'm just going to present this. This won't be on this might show up on the take home part. But basically when it comes to phase change, we talked about how the different phases have different levels of energy, right? What phase had the highest energy? Most energy in terms of energy of the particles? Would it be solid or gas? Gas, they're all moving faster, right? They're not stuck together as much. But there's an energy change associated with going from a low energy phase to a higher energy phase. And that energy is what we call that enthalpy of vaporization or enthalpy of fusion. And that is the energy required to change to vaporize a sample or a substance. So that's all well and good. How do we actually measure that? How does that actually show up in the real world? It's fine to talk about kilojoules per mole and things like that, but what does it actually mean? Well, it means that those phase diagrams, those phase changes that are happening at different temperatures are all governed by these energies. It turns out the Arrhenius equation that it references here is all has to do with what that energy is. And so let's see if I can do this one. Natural log of 1 over pressure is equal to minus delta H over R times 1 over temperature plus constant, which is delta S over T, delta S over R, I think. The reason that I'm actually spending any time on this, since I told you I'm not going to put this on the test, this is a really complicated equation. But what this actually tells us, though, is that it's not 1 over P, it's just P. That's what the issue is. That doesn't quite look right. This is actually looking at the vapor pressure versus different temperatures. So ignore that slide. That was just a prompt for me. What this actually means is that at different temperatures, you're going to have a different vapor pressure of a liquid or a solid. What happens when you get to where your vapor pressure is equal to atmospheric pressure, something boils. So you see a phase change when this number winds up getting high enough that it's equal to our atmospheric pressure. So we've talked a lot about in this class when we talk about phase change, about how up here at altitude, our phase change is different, right? Our boiling point is lower. And that's because our atmospheric pressure is lower. It's about 0.8 atmospheres instead of 1 atmosphere, which means that you get to a lower temperature in order to get this point where the vapor pressure is equal to the atmospheric pressure. It's more like 92 Celsius, not 100 Celsius. The other reason why I like talking about this this equation is that it's a really good example of some of the ways that we have to manipulate the data in order to make it form a straight line. So remember when we did that with the pressure versus volume of a gas, right? We plotted pressure versus volume, and we got something that looked like this, right? Like a 1 over X graph. And then we said, okay, well, what if we plot 1 over pressure versus volume? I think we had the axes flipped. If we plot 1 over volume versus pressure, we got a straight line. That seems kind of like cheating though, right? Because how can we just take 1 over volume? 1 over volume isn't a thing. Well, except that we can plot it on a graph and get a straight line. So it's a convenient mathematical approximation. Just because the math that's involved in getting the equation for a straight line is a lot simpler and more rigorous, meaning we can trust it more. And so we can actually do the same thing with this equation. If we look at this equation here as it's written, it looks like a mess. We wouldn't want to, who knows what that function is going to look like. If we just plot vapor pressure versus temperature, it's going to be something weird. But if we plot as a y equals mx plus b, we can actually get a straight line out of this. What would we plot? What variables would we plot to get a straight line? What would be the y value? We could take our vapor pressure at different temperatures and then take the natural log of it and make that our y. So instead of, if we actually plot this, let's see if I remember what it's going to, I think we're going to get a function that looks, we just plot temperature versus vapor pressure. We get something that looks like an exponential growth that then sort of like maxes out above a certain level. It's a really nasty function to actually try and do any math with, try and plot. We can't actually get the slope of this line because it's not a line. But if we take natural log of vapor pressure, and on the x-axis, 1 over temperature. Again, neither of these makes any sense on their own. But when we measure these numbers, take the natural log of them and plot them versus 1 over the temperature in Kelvin, we're going to get a straight line. It's not going to be proportional. It's going to have a negative slope, but it's going to be a straight line, which is weird. But it allows us to use stats to get the slope of the line. We can find a trend line if it's a straight line, right? And if we have a trend line, we can actually get that delta H value. So we can actually measure delta H. We can measure how much energy it takes to go through a phase change directly. Well, kind of directly. This doesn't seem like it's that direct of an approach, right? But from real measured numbers, we can actually get the slope. Once you have the slope, you have delta H. And so now this is one of my favorite equations to talk about, because this is one of the first places in chemistry and in science where you really have the theory and the real world, real measured data matching up. And one of the reasons that's so important is in chemistry, we don't get to measure things directly ever, really, right? We can measure masses and volumes, and that's about it. Everything else that we talk about in chemistry is some sort of abstraction, some sort of like connection upon a connection upon a connection. This is one of my favorite examples because you can measure vapor pressure and you can measure temperature and you can get this graph and directly measure delta H, which is kind of cool. I remember thinking it was kind of cool the first time I got to do that lab. We've done it in Gen Chem in first year chemistry before, but if you keep taking third year chemistry classes, you will definitely do this lab. In fact, it'd be like an intro lab to PChem, which is a really fun class. It's really hard. It's basically chemistry and physics and multivariable calculus all coinciding with each other. You get to do things like figure out by hand what the efficiency of an internal combustion engine is based on the internal temperature and the external temperature and what the fuel is. That's where physics and engineering and chemistry all come together. And that's the same class where you'd spend a lot of time talking about this equation. All that was just a fun aside. to get you thinking about phase change a little bit, just so we can change the subject. All right, let's talk a little bit about history. Y'all know I like science history. Radioactivity it was first called radiation, and the term for a lot of actually probably still to this day, radiation and radioactivity, the terms kind of get used interchangeably, but they don't actually mean the same thing. Because what's another form of radiation that we've dealt with in this class already? It's back before I got here, when you first did quantum and you were talking about graphs that looked like this. What is this number, or what does this value mean? Anybody remember? H nu. Energy of a photon is equal to a constant times that number. Yeah, I heard some. What is it? Oh, yeah, the flame tests. We did flame tests with the different colored flames. What does that variable represent? I'm really asking you to dig deep. Back, not just through winter break, but before Thanksgiving break even. Frequency. Frequency was that Greek letter nu. So the reason that radiation and radioactivity get kind of conflated sometimes is because radioactivity was first discovered because they saw new types of radiation, which just means light. All radiation is light. This fluorescents are putting out radiation right now. It's just in the visible spectrum, so we can see it. Any radiation is light. That's the definition of radiation. Think of the Latin roots for radiate. Actually, I think it's probably Greek. Radiate means give off light. So why did they call it radiation then? When they were really meant radioactivity? Well, because they first measured it. This is actually a really famous picture. It doesn't look like much, but this is because Henry Becquerel was given a piece of uranium ore as a paperweight by one of his former students. They were studying where you could find uranium because it was a newly discovered element at that time, and they didn't know really much about it. And one of his students gave him a chunk of uranium ore out of a sample from the way they used to get their uranium is they would just get literal metric tons of gravel shipped to France from Africa. And then they would go through it by hand and they would find chunks of uranium ore in there. So they found a particularly big, pretty one, and they gave it to their advisor as a present. I know, they didn't really know, right? Just a little light dose of radiation poisoning to thank him for all of his help in the lab. He set it on top of an X-ray film that was sensitive to light because he also did experiments that had to do with light. And so he used it as a paperweight to hold down this X-ray film. And when they then developed the film, it had this black spot that was in the shape of the rock. And there was no reason, they thought, for that to be there. So they started going down this rabbit hole of, well, what is it that something is giving off radiation? This rock is giving off radiation somehow. It's giving off light that we can't see. Why would it do that? What's going on there? And so this picture is really the first time that they discovered radioactivity. So Marie Curie was one of his students a couple years after that. And she was the one, along with her husband Pierre, who actually renamed it radioactivity instead of radiation. And she figured out that those rays, that high energy radiation that was coming out of these rocks was really dependent on only specific elements gave off this radiation. So this is Marie Curie and Eve and Irene. Irene on the right is the one that shared a Nobel Prize with her. I think we mentioned that before. And that's her younger daughter, Eve. She got to her first Nobel Prize was for her work in radioactivity and renaming it radioactivity. And her second Nobel Prize, which was in chemistry, was for discovering two elements. So and I know I've talked about her life story before, but it's really fascinating. If you want to go down a Wikipedia rabbit hole about 20th century science history, she'd be a pretty good place to start. Just read her life history on Wikipedia and see where you end up. If you don't wind up with like 7 open tabs by the end of it, then you're not spending very much time reading it, because it's really fascinating if you're into the sciences at all. And so we're going to stick for the most part to using the term radioactivity, right? And it's also just PSA. This is why you really shouldn't trust people that say things like, well, your cell phones give off radiation, and that's dangerous. Yeah, the fluorescents are giving off radiation too. It just means light. And the amount of radiation, or the frequency of the radiation given off by things like, do people still say this? This was a big thing when I first started teaching. Everybody was worried about, I guess 5G was a big deal, right? None of that really matters. All of the frequencies used by cell phones and microwaves and things like that are so low energy, they're below infrared in terms of energy, the radio waves. So they don't really they're not causing any damage. High energy radiation, like UV and above, can cause damage. Cell phones don't give off any of that, neither do microwaves. So don't trust anybody who tries to tell you that all radiation is dangerous, is the bullet point there. Because radiation, it does not mean radioactivity, no matter how many times they say it. Anyway, pet peeve of mine. Slash rain. There we go. So what is radioactivity? What is it that Marie Curie discovered? What she found out, what radioactivity is, and why it depends on what the element is in question is basically, under the right conditions, nuclei can break apart into pieces. And when they do that, you don't get the same particles out that you put in sometimes. And the mass will change. And that creates a huge amount of energy. Because if we're changing the mass, if we're looking at the actual mass numbers of these particles, the mass of a nucleus is not the same as the mass of its pieces, which sounds counterintuitive. Sounds like that's breaking conservation of mass. So like if I say, what's a good one? We use fluorine. Fluorine has a mass number of 19 and atomic number of 9. So how many protons does it have? 9. And then it's got 10 neutrons then as well, right? Well, the mass of a proton, 1.007 or so. And the mass of a neutron is 1.008. Which, that doesn't seem like it's that big a deal, except for the fact that this is more than 1 and this is more than 1, right? So if we have 19 of them, whatever our mass is should be more than 19, right? Even if we're not really looking at all the sig figs. What's the mass of fluorine on the periodic table? 18.998. So how is it that 9 times that and 10 times that adds up to 18.998? that math doesn't math. This is where we get to use that most famous equation. What's Einstein's most famous equation? E equals mc squared. Basically, this would suggest that conservation of mass is being violated, right? Because you're adding up these masses and you're getting a different number. Einstein was the one who figured out what's called energy mass equivalence. Basically, it's not the law of conservation of mass in the law of conservation of energy. It's the law of conservation of mass and energy. Turns out mass is just another form of energy. So that's what E equals mc squared is actually showing, is that the difference in energy, in mass, between what the pieces should add up to and what they actually add up to is the energy that's holding that nucleus together. It's called the nuclear binding energy. So we can actually do the math for this one. What should these pieces add up to? 19 something, right? So 9 times 1.007 plus 10 times 1.008. I get 19.143. And the actual mass is 18.998. So the difference between those two numbers. So I actually don't like this version of this equation because we're pretty much always going to be dealing with changes in mass or difference in mass. So in general, I think it works better to put delta in front of the energy and delta in front of the m. What is it? Whatever your change in mass is, times the speed of light squared, is going to give you your change in energy compared to all the pieces separate versus all the pieces in one nucleus. So our delta here is going to be, our delta m is going to be 0.3. I'm out of practice too. One something, one is it. I'm just going to get the calculator out, or you can help me out. 145. It is one. Okay. If we want to know how much energy is binding together these nuclei, we can take this number, we plug it in for delta m, multiply by the speed of light squared, and we're going to get an energy unit out. It's a little trickier though, because we need the units to work out. This is a physics equation, so we have to use physics units. What are physics units for mass?
10.
10. It's a good guess. Units, not numbers. What's a physics unit for mass? It's not AMU. It's not even grams. It's the bigger one, kilograms. So we need it in kilograms. So there is a conversion on your conversion sheet for AMU to kilograms. That would give you the mass in kilograms of a single atom. If we want to do it in terms of moles, we can also just write this as grams per mole. Which then that looks a little bit easier to figure out a conversion, right? Because we know what the conversion for grams to kilograms is. Divide by 100 or 1,000, right? So delta M is 1.45 times 10 to the minus 4 kilograms per mole. Anybody know the speed of light off the top of their head? Close. It's really close to 3. It's 2.998 times 10 to the 8 meters per second. Six, you might have been thinking of Planck's constant. Or guessing. So how much energy does it take to hold an entire mole of fluorine atoms together? We're going to square that. So it's going to give us something like 9 times 10 to the 16. We're going to multiply by that. So 10 times 10 to the 12. So it's something like 1 times 10 to the 13. 1.2 or so. Ish. .45 e to the minus 4 times 2.998 e to the 8 squared. .3 times 10 to the 13. Like I said, rusty. Okay, that's a big number, right? How does that compare, though? It's a big number, but we can make any number look big by writing it in the right units. Is it really that large of a number? If we put it in kilojoules per mole, get 1.3 times 10 to the 10 kilojoules per mole. So for comparison, burning gasoline is something like 1,600 kilojoules per mole. So 1 times 10 to the third. We are 10 to the 7 times larger than that. So 10 million times more energetic than burning gasoline. It's an absurdly large amount of energy. And it turns out when radioactive processes happen, the mass of the particles that come out are not the same as what you started with either. So this would be the amount of energy that it would take to split. If we wanted to take an entire mole of fluorine atoms and split them all up into individual protons and neutrons, we would have to put in this much energy. This is, let's see, what was that graph? I want to say that this is comparable to the amount of sunlight that hits the Earth, the entire Earth, in a second. So picture taking all of the energy from the sun that hits the entire Earth in 1 second, just to do 1 mole of fluorine. Just take 19 moles or grams of fluorine and split it up into pieces. It's really, really a lot of energy. This is also why when Einstein first discovered this and they first started thinking about, well, anytime humans find new science or new technology, what's the very first thing they try to do? Especially if you're in Europe in the in between World War I and World War II, you weaponize it. At least if you stick to most of human nature. Yeah, so the very first thing that humans tried to do after Einstein discovered this was, well, how can we turn that into a bomb? And then, granted, it still took them another 15 years before they were actually able to do that. But this is what got the ball rolling, so to speak. And in fact, during World War II, this equation and numbers like this that seemed absurdly large, why pretty much the entirety of the scientific community in Western Europe and in North America all signed a letter to Franklin Roosevelt urging him to basically start the Manhattan Project, what turned into the association from Oppenheimer, the movie, was because they wrote this letter to FDR saying, hey, this is a really big number. And because it was a really big ask. The last thing on anybody's mind in the military and in politics during a war that's depleting all of your country's resources is, well, let's take a huge amount of money and put it towards this theoretical technology that may or may not ever work. That was a really big ask. But because it was Einstein and because these numbers were just so big, FDR started the Manhattan Project and started that whole research endeavor. You guys know they built an entire city effectively overnight in Tennessee. Oak Ridge, Tennessee did not exist until the Manhattan Project started. Why? Because that's one of the places they were refining the uranium. There were a couple of pieces to building an atomic bomb during World War II. You had to get enough plutonium or uranium, and then you had to refine it to weapons grade, and then you had to put it into the right configuration and design the bomb. So what they actually did in New Mexico and Los Alamos was actually designing the structure of the bomb. But the actual refining happened mostly in Berkeley and Oak Ridge, Tennessee. And then they shipped it to Los Alamos for the Trinity tests. If you haven't seen it yet, Oppenheimer's definitely worth a watch. It's pretty accurate as to the science. The other thing you could do is one of the junior scientists who gets a little bit of screen time in Oppenheimer, but he was a generation behind the Einsteins and the Oppenheimers, is Richard Feynman. He has a really good autobiography called Surely You're Joking, Mr. Feynman, where he talks about his time at Los Alamos. He was one of the ones actually like doing the hands-on stuff, not one of the ones doing the theoretical stuff at the time, I believe. All right, back to what does this actually mean for us today? These nuclear reactions, these radioactive reactions, are any reaction that changes the nucleus. It seems easy enough, right? It's a nuclear reaction because the nucleus changes. That's what's different about nuclear reactions compared to all of our other reactions up to this point. All of our other reactions up to this point have been, we balance them by just looking at how many atoms we have on both sides, right? So if I did something like combustion of methane, we balance it by just making sure we have the same number of carbons, same number of hydrogens, same number of oxygens, right? Gotten pretty comfortable with that, even if it still is a little bit dicey sometimes on the trickier ones. Nuclear reactions, that's not what happens, because in a nuclear reaction, you don't end up with the same number of carbons before and after. So for instance, see if I can get this one right off the top of my head. Our carbon 13, when it decays, carbon 14, when it decays, it turns into nitrogen. How does that work? It's no longer balancing the same way. Basically, there must be some other pieces happening in there. We still are going to balance some things, but it's not as simple as count the number of nuclei anymore. All right, and so mostly these reactions fall into two categories. Fission reactions are when you're splitting big things up into smaller pieces. And fusion reactions are the exact opposite. So, uranium-238. naturally will undergo a process called alpha decay, where it basically loses what's called an alpha particle. We use the Greek letter alpha for it, lowercase alpha, that has a mass of 4 and 2 protons in it. How many protons does uranium normally have? One time we actually need the bottom row of the periodic table, right? I think it's 92. Check your periodic table. It's taped to the side of the desk you can't see. Down at the bottom, right? Is it 92? Basically, when uranium goes through a fission reaction, a chunk of that nucleus breaks off. 2 neutrons and 2 protons break off of that nucleus, and we get a new element. What is uranium that's missing 2 protons? And check your periodic table. If uranium was missing 2 protons, what would it be? Thorium. It would have a mass number of 90 now. So if it lost 2 protons and 2 neutrons, what's the new masses of the thorium now? It was uranium-238. You lost 2 neutrons and 2 protons, so your mass number drops by 4. So things still kind of balance, except now instead of balancing nuclei, we're balancing your total number of protons and neutrons. Your total number of protons and neutrons is not. Your total number of protons plus neutrons is not going to change. But whether they're stuck together as one big nucleus or if they start breaking apart into smaller pieces is going to determine what elements you have. All right, so this is the process that happens naturally on Earth as well. All uranium on Earth is going through this process at all times. That's why uranium is constantly giving off dangerous radiation, is because the radioactive process where it breaks down into thorium and then from thorium into other things is continuously happening. It's just happening really, really slowly. The half-life of uranium-238 is something like 4.5 billion years. So if at the beginning of the solar system, if you had 100 kilograms of uranium-238, by now you'd have about half of that left. Half of it would have decayed into other stuff via this process. The other half would still be waiting to decay. In another 4.5 billion years, half of what you had, so you'd then be at a quarter of what you started with. All right, so what's the opposite process? When you slam stuff together hard enough that it sticks together. So fusion happens when you get nuclei so close together that instead of just pushing each other apart, because normally we'd say, okay, well, if it's a nucleus, it's got a positive charge and another positive charge, right? If we force them to go towards each other, they're going to push each other away, right? If you slam them together hard enough, they stick, they merge to be a larger nucleus. That's what a particle accelerator does. You've heard of particle accelerators like in CERN in Switzerland and in Palo Alto. All particle accelerators do is they get things going up really, really fast, and then they direct them onto the same track and slam them into each other. And then look at what happens. Sometimes you get a totally new element when that happens. Right? Remember that nuclear binding energy that we were talking about for fluorine? The reason that fluorine exists at all is because of that binding energy. When you slam these things together and they stick together, it releases even more energy sometimes. And that's what a fusion reaction is. All right, where's one place in nature that we see fusion reactions happen all the time? I'll give you a hint. It's not on Earth. Wrong direction. The sun. The sun's a giant fusion reaction. It's just an ongoing fusion reaction where because you got a whole bunch of particles together, the force of gravity is enough to jam them together like this and start making new elements. That's kind of cool. In fact, Jupiter is not that far from the threshold of becoming a star. Jupiter is the next largest thing in our solar system, right? In fact, if you look at the relative mass of all the planets in our solar system, astronomers are fond of saying that the solar system is the sun, is 99% the sun, and 1% Jupiter, and the rounding error. Right? Because Jupiter is so much larger than everything else in the solar system besides the sun. And one of the, if it was, I think it's about 50% larger, then Jupiter would qualify to be what's called a brown dwarf, which is basically a star that's, it's not a full-blown fusion reaction like sun, but it's giving off enough fusion energy. There's some fusion happening at the core that gives off energy. But that's what our two basic categories are, though. Right? So fusion reactions happening in the sun, anytime you get a large enough mass together, or in case of Earth, we can actually have fusion reactions happen here. We can't do it sustainably. We can't keep a fusion reaction going on Earth at this point. Does anybody know what kind of fusion reactions, where you see fusion reactions on Earth in human technology? You don't want to ever see one of them. A bomb, because what do humans do? When we get new science, we make bombs. So if you've ever heard of a thermonuclear weapon or a hydrogen bomb is a fusion reaction. You have to use regular atomic bombs to start the fusion reaction. But when you do that, you get something that's about 100 times more dangerous than just a regular atomic bomb. We are really good at finding ways to blow ourselves up. So, for context, the smallest nuclear bomb ever detonated was the first one ever detonated over Hiroshima. And it was the equivalent, I want to say it was either 10 or 15 kilotons, which doesn't sound like that's that big until you break down what that number means. 10 kilotons. That's tons of TNT. So 1,000 kilograms of TNT is 1 ton. And then we're talking about a kiloton. So 1,000 tons of TNT. This is one bomb that released the equivalent of 10 times 1,000 times 1,000 kilograms. So like 10 million kilograms of TNT detonating simultaneously. And that's the smallest one of these that we've ever detonated. There it is. The biggest is called Tsar Bomba. It was named by the Russians. It was the king, which literally translates to king bomb. I want to say that the one they built one that was 150 megatons. So a megaton would be another 1,000 times larger than a kiloton. They detonated one in the upper atmosphere as a test that was 80 megatons. So just for reference, there's actually a Google Maps plugin that lets you plug in, like, what if we detonated a nuclear bomb here? How far would the blast radius be? What would how far out would it? And it would basically, if I'm remembering right, if you detonated Tsar Bomba in Reno, it would break windows in Placerville. Assuming that the concussive force could go around the mountains, it would actually be more kind of like a rain shadow effect because of the mountains. But basically, think about, 150 miles away, you're breaking windows. And everything within about 40 miles, so everything from downtown Reno to Minden would be gone. And we luckily would probably just be dying of radiation poisoning and burns. You get third-degree burns in South Lake Tahoe if you were outside when that happens. Let me see if we have time at the end. A couple things I want to go over. All right. So here's your basic types of radioactivity. So not everything decays the same way. Not every radioactive element goes through that same alpha decay that we just talked about. Alpha decay was the first one they discovered. It's one of the most common because basically as soon as you get larger than bismuth, turns out everything larger than bismuth is inherently an unstable nucleus. Literally everything on the periodic table that's larger than bismuth is radioactive and is constantly going through a radioactive decay, most of which is alpha decay. Turns out once you get a large enough nucleus, the strong and weak nuclear force can't counteract the fact that you've got all these protons pushing on each other, and protons push other protons away. So the most common type of radioactive decay that we see in nature, anyway, on Earth, is this alpha decay. And so this alpha decay, here's just the same reaction that I wrote up on the whiteboard a second ago. If you have a big nucleus and it goes through an alpha decay always looks the same. You're going to make, so we'll do the same thing with thorium-234, because thorium-234 also goes through alpha decay. But basically what you get is a helium nucleus, which is also called an alpha particle, flying out from the nucleus. It flies off on its own with a really high energy, a lot of speed and force. All right, so if it was thorium-234, you don't have to write the number of protons, but it can be helpful for reminding yourself what the different products are going to be. If thorium-234 went through an alpha decay, it's going to make an alpha particle, which you can also write as helium, the way it is on the slides. We kind of use alpha just as a way to indicate that it's coming from a nuclear decay, not coming from just as a helium on its own. What would be the other piece of this be? When thorium breaks up and gives off an alpha particle, it's going to turn into, how many protons does it lose? 2. So what's thorium missing 2 protons? Is it radium? I think it's radium, not radon yet. Radium will decay into radon after this on the next step. Right, so if it goes through an alpha decay, you just take what you started with, make an alpha particle, and then whatever's left, whatever pieces are left, because you still need this to add up to 234 with 90 protons. So do it one more time. Now what do we get? Still another alpha particle. Now it's radon. Right, because follow on the periodic table. If you look at radium, 88 in the bottom left corner, when it gives off 2 more protons, now it's 86, which is radon. This is why certain parts of the world have a problem with radon gas, because if you look at the geology of those areas, they tend to happen, well, one, near fault lines, but also in areas where there was a lot of uranium in the soil or in the Earth's crust in that area. Because over a long enough time period, that uranium, which starts as a metal or as an ore, turns into thorium, which is also a metal. So it stays as an ore. Turns into radium, which is also a metal, stays as a solid. But then the radium turns into radon, and radon is a gas because it's in the noble gas column. So radon gas starts to accumulate in the Earth's crust, and it tends to show up where we have active fault lines because it's basically like creating cracks that allow the radon to escape. But also in areas where you had larger than average concentrations of uranium. Turns out uranium is almost uniformly distributed throughout the entire planet crust, but there are certain spots that have slightly higher concentration than others. In those areas, fast forward a couple billion years, and you get radon buildup in basements and things like that. Fun fact about radon: it's heavier than air. So you know how helium, when you breathe helium, your voice goes up, right? Because your vocal cords vibrate faster because the gas is lighter. Radon's heavier than air. So it goes the other way around. You can make your voice really, really deep if you use radon. Although you don't really want to breathe radon. It's not a great idea. There are safer options for doing that. I want to say it's selenium hexafluoride, sulfur hexafluoride, or selenium hexafluoride. It's also a gas. It's likely. So this is my standard response when people ask about most carcinogens. The number one carcinogen on Earth is not sunlight, actually. It's oxygen. So if you really want to avoid all carcinogens, just stop breathing and going outside. It'll be real fast. You won't get cancer.
Plus, what antioxidants, you guys? Oxidant is going to kill you.
The oxidant is oxygen.
That is true. Promise we need that activity to power the chemistry that keeps us alive, but that same thing, it bursts through the process. That's what aging is.
So,
yeah, that's fast.
Because the electron transport chain transfers a single electron at a time, you get peroxides in your body. Anyway, take biochem if you want more of that. Biochem, you get to learn all about the electron transport chain.
Yeah.
All right. A couple more things so that you can do your assignment for tomorrow. We talked about alpha particles. Other types of naturally occurring radioactivity get real weird. So a beta particle, we named the first one's alpha, so the second one we named beta. The beta particle is basically an electron, except it's an electron that comes from the nucleus. We spent this whole term learning about how electrons are around the nucleus, not in the nucleus, right? It turns out you can spontaneously create electrons if you go through the right process. So basically what happens is if you start with carbon, it is carbon 14. I had that one right. Carbon 14, basically it starts with 6 neutrons, or sorry, 6 protons because it's carbon. Basically, one of those neutrons can turn into a proton. If you took one of those neutrons and you turned it into a proton, it's not carbon anymore, right? Because our elements are defined by how many protons are in the nucleus, right? So if we add an extra proton by converting this neutron, one neutron, into a proton, we get nitrogen. It still weighs 14, still has a mass number of 14, because we still have the same number of pieces. We just took one of the neutrons and turned it to a proton. Basically, it's to get in, take a theoretical physics class or modern physics where you start talking about quarks. But basically, a neutron can turn into a proton if you switch one of the quarks from being an up quark to a down quark, or the other way around. I don't remember because I'm not a theoretical physicist. But if you flip one of those quarks around, the quarks are what have the mass. So you still have the same mass, you still have the same number of quarks, but you change the charge. You change it from being a neutron to being a proton. And in doing so, it generates a beta particle. It generates an electron that has a mass of 0. Well, close to 0 because it's an electron and it's really small. It seems like the easy way to think about this would be like, oh, well, a neutron must be like an electron stuck to a proton and we're just ripping off the electron. It turns out the reality is more complicated than that. It's more like, remember when we had electrons and we had them 2 different energy levels and one of those electrons fell back down? That gave off energy, right? Go back to the flame test lab. When you did that, it made a photon out of nothing, right? It generates lights from nothing when you go from a high energy state to a low energy state. This is sort of the equivalent, but in terms of strong nuclear force instead of electromagnetic force. In strong nuclear force is most stable when you have the right ratio of neutrons to protons. If you don't have the right ratio, that's like being at a high energy state. If you let it fall down to the lower energy state, it generates an electron this time, not a photon, which is weird. And again, this is physics because we're talking about strong force and weak force, not electromagnetic, but it has some parallels. But we can still balance these. If you know that a beta particle is going to have a mass of 0 and has a charge of -1, everything still balances. Your total number of particles is still 14. And the number of positive charges in the nucleus is still going to add up to the same number because you've got a 7 and you've got a -1. Still adds up to 6. Right? So there you go. So beta particles are weird. What do? Once we get a handle on one weird thing, we make it weirder. We're going to do the same thing, but with antimatter. So it turns out you can have a beta particle that's positively charged. Let me go to the next slide. So I get my example right. So phosphorus. Phosphorus will do this. Phosphorus 15, or sorry, phosphorus 30. It'll go through a similar process where you get a charged particle with next to 0 mass flying out of the nucleus. Except it's positively charged. We still write it like it's a beta particle, but it's got a +1 instead of a -1. Which is weird, because what I just described was an electron with a positive charge, right? Turns out that's what antimatter is. Antimatter is just matter where all the charges are flipped. So everybody's, maybe not everybody spent their junior high years reading bad sci-fi. But antimatter is probably a term you've heard before, even if you had no idea what it was. That's what antimatter is just regular stuff, same periodic table even, same properties, except the charges are reversed. And that means what we made here is not an electron, it's the same mass as an electron, but with a positive charge, so we call it a positron or an anti-electron. If it's easier to remember, you can call it an anti-electron. Right? So if we can't tell, if antimatter has all the same properties as regular matter, just with the charges flipped, there's actually a lot of antimatter in our universe. We can't measure it though. We can't even really tell what's antimatter and matter, regular matter, once we get far enough away, because how do we actually measure like another solar system? We look at what light comes from it, right? If all the physics is the same and all of the energies are the same, just with the charges flipped, we actually can't tell the difference between a galaxy made of antimatter and a galaxy made of regular matter. Because how could you measure that? If all of the light is the same, we don't have a way of measuring it other than by looking at how light comes off of these things, because nobody's going to another galaxy anytime soon. So in theory, if you add up all the regular matter and all the antimatter in the entire universe, it would add up to 0. So basically, matter exists because it's more stable existing than not existing. But if you took all the matter and all the antimatter in the entire universe and brought it all together, it would add up to nothing. Because when antimatter hits regular matter, they disappear. And they turn into pure energy, according to E equals mc squared. He's been wrong about a lot of things, but not about this. I think this was more Hawking's than Einstein at this level. When we get to the antimatter. It doesn't, other than when it runs into its counterpart, it disappears and turns into pure energy. Yeah, antimatter bombs it's coming. All right. Last point. I know we're almost out of time. Last 2 points. You get the same net effect making a positron by basically getting an electron that gets too close to the nucleus, and it basically sticks to the nucleus. It's called electron capture. Electron capture is going to have the same net result, where if you take your electron and write it as a beta particle with a -1 down here, you're just going to add everything up. So it's still going to be a mass of 92. It's just our atomic number changed from 44 to 43 because an electron got stuck to it, basically. It's canceled out one of the protons. The last type of radiation, radioactivity. Gamma radiation. As made famous by Marvel. Gamma radiation, what made the Hulk, right? Basically, gamma radiation is not its own type of radioactive process. It's a byproduct of all of the other 4 that we already talked about. Right, so most of the reactions that you're going to see are going to be one of these top 4: alpha particles, beta particles, positrons, or electron capture. Gamma rays, that's just a type of light. That type of light happens anytime you've got a process that gives off enough energy fast enough. So gamma rays of different frequencies are going to happen with all of these others. The harmful high level or high energy radiation that shows up as a result of radioactivity is usually in the category of gamma radiation. So they call it gamma rays. And because that's the actual X-rays that Becquerel was first noticing with that paperweight, that's why it got conflated, because the only place in nature that you saw X-rays was from uranium ore, was from radioactive processes. So for a long time, those two words, radiation and radioactivity, got conflated. Because all radioactive processes will give off some form of radiation. But not all radiation is harmful, and not all radiation comes from radioactivity. Because radiation just means what? Light. Right, so I just put that one in there because it still gets referenced a lot. Gamma radiation, that is the Greek letter gamma. Looks like that little squiggly Y. In the handwriting, it usually looks like that. Is just a byproduct of these other four. Now, there are other processes that can happen. We haven't even touched on fission reactions that lead to a nuclear bomb yet. But basically, if it's not one of these four, I have to tell you what it is because it's kind of hard to predict. So I will on the test, I'll say something like uranium-238 plus a neutron goes through fission, and these are the products right out the reaction. But I have to tell you what the products are. For these four, your assignment tomorrow is basically going to be, here's a radioactive isotope that goes through this process. What are the products? Write it out. Right, so basically what we were practicing today. And then we'll get practice with the math behind all this on Thursday. All right. We would probably see signs before we got there. So what would happen is around an antimatter solar system, all those particles, there's super pressure. So they're going to start running colors. Start to see. Maybe that there's a way that I don't understand, but as I understand it, everything's totally identical except the charges. It'd be really unlikely. I know that most of our part of our solar system, matter because it would have disappeared. So it would be galaxies where you're galaxies could be matter and antimatter because they've got a large separation, but I don't even think that it's likely that we have a planetary system that's antimatter anywhere in the Milky Way because it would have gotten something in some way.
So it's like antimatter. There's like everything on like that we know right out in like
yeah,
but then like antimatter is theoretical.
So we can observe positrons. We can see this happening, and then when they run into an electron, they vanish and get a ton of energy. And there were actually some researchers in Berkeley that managed to make like 1/10 of a gram antiproton. It's like a kind of a lot of antiprotons by theoretical physics standards. And they used a really super high vacuum and magnets to keep it in place so it didn't touch anything else. And it lasted like half a second before it strengthened and then it disappeared. It is. It's weird.
Times at UNR,
Thank you.
they have some of their like students in like something like